Good evening, students. In yesterday class, I discussed the criteria for phase equilibrium. First one is a thermal equilibrium. Thermal equilibrium, that is all the phases temperature is same, or the heat flow from one phase to another phase. The final equation is TA is equals to T. Yesterday class I discussed up to here the thermal equilibrium. In today's class I am going to discuss about second one, mechanical equilibrium. Mechanical equilibrium. In this mechanical equilibrium, all the phases of a system are under the same pressure. In all phases, the pressure is same. In any system, you have to consider in mechanical equilibrium. In all the phases, the temperature in this the pressure is same, and otherwise volume of any one phase will increases, or while that of other phase decreases. Here all the phases are any system, all the phases are under the same pressure. In this same pressure, and sometimes here the phases are increases or phases are decreases. You have to consider a system. This is the system. You have to consider the system. This is a phase A and this phase B. Here the all phases, the phase A, phase B, phase, in all the phases the system is, in this system the pressure is same. Here the phases are increases or the phases are decreases. In equilibrium at constant volume and temperature. Here temperature is constant and volume is constant. In yesterday class I taken this is a PA and this is a PB. Here PA and PB are the phases. PA is the pressure of, this is the system. PA and PB. PA is the pressure of phase C. PA is pressure of PB is the pressure of phase. Here I taken volume D. This is the change in here volume is taken, that is small amount of work. Here, this dV is the V is the volume. This is a small amount of here the phases are decreases and the phases are increases. First one, increases phase decreases phase. This is the condition. dV is the small amount of volume where phase increases in phase A, decreases in phase B. Next, according to thermodynamics, the work done is W is equals to, considered according to thermodynamic criteria. Thermodynamic criteria, work done is W is equals to P into dV is here I taken dV is small amount of volume. P is a pressure constant, W is a work done. And here that work done is a dA. This work done is dA of A and dA of B. These are the work done. I taken change in work function of phase A. Change in, consider this is a work function and change in work function of phase A. Changing work function of phase A. If A is equals to, that is here first one PA, PB, TV, and this is a according to thermodynamics. According to thermodynamic, W is equals to P into dV, and here the change in function of phase A, the change in function of phase work functions, change in work function. Change in work function of phase A, that is dA of A. Here dA of A is this PA of dV. You substitute here d of A is work function of phase A, that is dA of A is equals to plus PA into D. This change in volume, here change in work function of phase A, and change in work function of phase B is, here you have to take A of B, dA of B is equals to minus of PB D. I write here change in work function of phase B, that is d A of B is equals to minus P V of D. And next, at equilibrium, here this is a change in work function, this is a change in work function of phase A and phase B. And next you have to consider at equilibrium the change in free energy. At equilibrium, the change in free energy. Change in equilibrium means it is zero. That is dA is equals to change in equilibrium. That is dA is equals to this one and dA dB. dA is equals to, that is here, dA of A plus dB A of B. That this is a phase here and this is a phase B. Final at equilibrium, change in free energy. This is change in free energy. Here change in work function of dA and change in work function of dB. Substitute this one dA and dB. Here I substitute here. dA is equals to this one PA dB minus of PB dB, and this is at equilibrium state here, that is dA is equals to dA is equals to 0. Here PA dB minus PB dB is equals to 0. Final equation PA dB is equals to PB dB. Here the negative sign indicates decreases. PA dB is equals to, this goes to this side, PB. Here this is. Finally, PA is equals to PB. Here the pressure of phase A, the pressure of phase B are same here. The all phases of the system, the pressure is same here. This is the conclusion is here, that is the pressure is same in all the phases. This is a mechanical equilibrium expression. In first thermal expression, in thermal equilibrium, temperature are equal. In mechanical equilibrium, pressure are equal. Third one, chemical equilibrium. Chemical equilibrium. The chemical equilibrium. In chemical equilibrium, defining the chemical potential of any component. Here, the chemical potential, in the chemical potential of any component must be same. Any component must be same in all the phases. In all the phases, the chemical potential of any component is same. This is called thermodynamic criteria for phase equilibrium. What is meant by phase equilibrium? Sorry, Thermodynamic criteria for phase equilibrium is the chemical potential of any component must be same in all the phases. This is called as thermodynamic criteria for phase equilibrium. In this chemical equilibrium, the chemical potential is change in free energy which takes place at a constant temperature and constant pressure. Temperature and pressure. Here change in free energy it must which takes place here constant temperature and constant pressure, and when one mole of component is transferred from one phase to another phase. We have considered one chemical composition, and in this is a C1, C2, C3. These are number of chemical components here. One mole of component it transferred from the another phase. One mole of component changes are transferred to the one phase to the another phases. See here. This is a system. C1, C2, sorry, C1, C1, C2, C2, C3, C3, etc., etc. Cx, a Cn. This is a phase A, and this is a phase B. Here, this is a component, this first component. Here, this is a first component. In this, one mole of component is transferred from the other phases of the component. One mole of components. Here, one more component is transferred. This is two phases. Here, I have considered the two phases and number of components. I taken the temperature and constant phases and temperature and pressure are constant. Next, I write here D. We have considered the amount of component one is transferred from phase A to phase B, or one phase to another phase. I taken dn1. dn1 is the amount of component 1 is transferred from, this is the amount of component 1 the amount of component 1 is transferred from A to B, or phase A to phase B. Phase A to phase B. And next, this constant, that is the mu, and mu1A, this mu1A means here, that is the chemical potential of component 1 in the phase B. mu1 is chemical potential. Chemical potential of component 1 in chemical potential of component 1 in the phase A. In the phase A. Next one, mu1B. This is considered mu1 A, and second mu1 B is a chemical potential of component 1 in the phase B. This dN1 is the amount of component 1 is transferred from phase A to phase B, or one phase to another phase. Mu1A is chemical potential of component 1 in the phase A. Mu1B is the chemical potential of component 1 in the phase B. And decrease in free energy component 1. This decreasing and increasing in phase A and phase B. Increase in free energy. I write here. This mu1 A 1. This is a decrease in free energy. You get a negative sign, decreases. This you get a positive charge, it is a increases. First one, decrease in free energy of component. This mu1 A D N1, decrease in free energy of decrease in free energy of component 1. Decrease in free energy of component 1 in phase A. In phase A. And second, I consider that is mu1 B dN1. Here, this is a negative. Here, increase in free energy of component 1 in phase B. In phase B. Free energy change. This is a decrease in free energy. This is an increase in free energy. What is meant by free energy? Free energy change is the sum of these changes. Sum of the changes of various phases. And I have told here dg is equals to dg. Here, this is a decrease in free energy. These are some of these. Here, dz is equals to free energy change is the sum of increasing free energy of component 1 in phase A and increasing in free energy of component 1 in B. Here, dz is equals to dza plus dgb. And according to concept of partial molar free energy, that is here dz is equals to 0, because here at constant temperature and constant pressure, that is dt is equals to 0 and dp is equals to 0. Therefore dz of this also write dz of temperature and pressure are constant. Here temperature and pressure constant, that is dT is equals to 0 and dP is equals to 0 and this is 0 here. That is dz of temperature pressure is equals to this one minus of mu1 A dn1 plus here plus mu1 B dn1, and this comes to this side. Here this is a 0 is equals to minus of mu1 A dn1 plus mu1 B dn2. Sorry, n. Next this comes to this side. Mu1 A dn1 is equals to mu1 B dn1. Here dn1 dn1. Only final equation mu1 A is equals to 1. This conclusion. Here all the phases, that is the mu1 A is equals to mu1 B. Here the conclusion, that is a component is distributed in a phases, the different phases. Here a multiple system at equilibrium. This is a multiple system. The phases are constant. Component is here constant. Mu1 A is equals to mu1 B. Chemical potential are equal. Here any phases, any number of phases. You have to take another I, A, B, C. In general, I have to write here in I, mu I A is equals to mu I B is equals to mu I. This is a chemical equilibrium. For a multiple system at equilibrium, the mu of a component I is same in all the phases. This mu is the same in all the phases. I stop class here only. Next class, derivation of phase law. Derivation of phase law. I continue this derivation in the next class tomorrow at same time. Thank you.